Okay, thank you, Saf. Welcome everyone for our fifth lecture in the course Deep Learning for Computer Vision. This talk will be about object detection and image segmentation. So what we covered in the previous lectures was the basic task of image classification in the context of deep learning. So we have plenty of training images, all ImageNet. Whoops. We used deep networks or deep convolutional networks as the model for our classification. We tried cross entropy to match the predictions and the labels that our images are labeled with. And we used stochastic gradient descent to find the best parameters of the model of the deep network that fits this task. And now that we know how to train image classification networks, how to use them, what kind of image classification networks there are out there, we can move forward to more complicated tasks. So the additional tasks we're going to talk about today are object detection, which is the task illustrated here. We might have more than a single dominant object in the image, like cats, dogs, ducks, whatever, and we want to pinpoint each and every one of the objects. We want the network to draw a tight rectangular around each and every one of the objects. You can think about even more accurate delineation of the objects, like semantic segmentation. We want all the pixels of the cats to be differently labeled than the pixels of the dogs and the other objects. And we can ask even further, if we have several instances of the same object, of the same category type in the image, we want to make them segment separately. So we want all these pixels to be cat pixels, but we want the model to know that this cat is different than that cat. There are two cats here, and we want to segment them separately as different cats. So these are detection, semantic segmentation, instance segmentation, and we'll talk about them in this class. So we'll start with object detection. First thing we need is training data. And currently the most famous and mostly used object detection and segmentation dataset is called MS-COCO, Microsoft Common Objects in Context. It has 200,000 labeled images. In these images, there are 1.5 million instances segmented, as you can see here in the examples. And they have 80 object categories. You can see these categories here, from utensils, objects for indoor, animals, outdoors, whatever. And one thing we might wonder at first glance is that 200,000 images is very small compared to the million images we had in ImageNet. But once we think about it, it actually has 1.5 million instances. So it's true that we have fewer images, but we have much stronger supervision here, because for each image, we have more than a single label. We have different object types and different regions in the image. So basically, despite the fact that there are fewer images here, this data set is richer, in fact, than ImageNet, and is more useful. So let's talk about object detection. So why object detection is so difficult once that we know how to classify images? So if we have image classification, we can know how to classify image into 1,000 categories. What's so difficult about finding 80 object types in it? Can't we just switch the output vector of 1,000 dimensions into something that can classify it into objects? So it's not that simple. First of all, we have multiple types of outputs. So we are not only outputting label the class of each and every one of the objects. We are not just doing classification to cat and dog and duck. We also want the bounding box as an output. So we have both discrete labels and the continuous bounding box as the output types of the network. So it's a network that should do both discrete classification and continuous regression for its outputs. And another thing that is very challenging is the fact that we don't know in advance how many objects there are in the image. So in image classification, we knew we needed to output one label for each and every one of the images. Now we need to output different number of bounding boxes and labels for each and every one of the images. Additionally, in image classification, we assumed a fixed and very small image size. So most of the image classification networks that Dror showed you in the last tutorial treated all images as 224 by 224 pixels. So if you had a bigger image, that you just scale it down, you crop the center of it, and you work with these fixed size images. But for object detection and segmentation, we usually want to work with larger images that has more than a single object in them. And we're talking about, so there's also the additional computational burden that we need to take into account. So how are we going to address these challenges? So let's start small. Let's start just with how to output two types of predictions for each and every one of the labels. So we focus on a slightly more easier task than detection. We want to do classification and localization. So suppose we have a single dominant object in the image, like in image classification, but now we want the network to predict not only the class of the image, but also the bounding box around this object. So we want the object to localize, the network to localize the object. So how are we going to address this simplified task? We can use an image classification network that has convolutional networks and convolutional layers and pooling layers, and it outputs a feature vector in some feature dimension. And what we used to have is a fully connected layer from this feature vector into 1,000 categories. Now, what we can do is use the same feature vector X, which is the latent representation learned by this backbone. And we apply another layer from this feature space into 4 coordinates, which are the corners of the bounding box. And we are going to train this class prediction with cross entropy loss, and this continuous bounding box corners with L1 regression. Okay.
Why L1?
It's regression, so you can use L1, L2, or smooth L1, but it's not cross entropy. That's the key point here. It's a different loss because it's a different kind of task. So it doesn't have to be L1, but it can't be cross entropy. That's the main point here in the slide.
Shai, what is WF and WF hat?
So these are the weights of a fully connected layer. So we have, suppose this is VGG that Dror showed you. What a deep convolutional neural network learns, as Asaf already taught you, it's basically transformation into some meaningful feature space in which it is very easy using linear classifier to classify the object or the image. But we believe this feature space is rich enough that it's not only helpful for classification, but it will help us to localize the object as well. So since this is a convolutional network, it's translation equivariant. If we move the object, the features will also be translated accordingly. So there is information about the location of the object, and we should be able to train this simple linear layer to regress and find the corners of the objects if we have proper supervision.
So
Shai, I have some general question. When you train with more than one loss, in this case, 2 losses, so when you do the backpropagation to learn, so you do it twice? I mean, one for the first loss and one for the second loss?
Excellent question, because this is the next slide. So indeed, as Dana asked, how can we apply stochastic gradient descent if we have multiple losses? If we have, actually, we have a vector function as the loss function. So we know to compute a scalar gradient and do gradient descent with a scalar function. It's not really possible to do it with a vector function, because now there might be a contradiction between these two. So we need a scalar function, and the simplest thing to do is basically combine them. So we have one loss function, a scalar, which is a linear combination of these two. We have a weight that weights between the two. Okay? So if we combine things, so we do the math and we just add a plus sign, but if you ask someone from the physics department to combine two terms, they'll ask you what are the units of measures. So we are actually putting together apples and oranges here, and it needs to make sense. So what are the units of measures of cross entropy?
Bits.
Bits, yes. To be more precise, it's nits. It's because we are not using base 2 logarithm. We use the natural logarithm, but yes, it's bits because it's information, which measures how much information we have about the class from our network compared to some random guess. And what are the units of this loss?
Pixels?
Yes, pixels. So we're actually adding bits and pixels, and this coefficient needs somehow to balance between them. So if we want this to be very close to 0, meaning we emphasize more on getting the class right, and we are less concerned about the accuracy of the bounding box. And if we want to be more accurate about finding the objects and we don't really care if it's a cat or a dog, then we'll put this lambda to be very high value. But now we have a scalar loss function. How does it backprop? So when we backproject things, so the gradient of the cross entropy with respect to these weights of the localization is 0, because these weights don't affect the cross entropy. So whatever mistakes we made with the cross entropy, it won't affect these specific weights of the localization, and vice versa. So any mistake we did about the localization won't affect the cross entropy, but the features which are shared by both these tasks will basically see a combined gradient of these two losses. So we are trying to optimize this backbone to have features that are useful both for classification and for localization. Okay?
Yes, I can have a question.
Yes, of course.
Do we use classic deep convolutional network? Because most of them lose resolution as we go forward.
Okay, we'll get to that much later during this talk about resolution and resolution trade-offs. But yes, essentially, you can what usually people use are image classification backbones. This is why it was so important to have Dror's tutorial about different architectures. So it's not just a survey of nice work people did about image classification, but basically all these backbones are used for more complex tasks like classification, segmentation, and whatever. Very important, because the features you learned in image classification and the architecture you're using to learn these meaningful features can be easily used for other tasks in the form of this backbone that gives you very informative and useful features. And just a side note, we are doing here multitask learning. So we have 2 tasks and we are training a single network with 2 tasks. And it's considered very good practice, even if you're only interested in one of the tasks. So if you're trying to do image classification, but your data has more labels other than more types of labels. So it has bounding boxes, it has attributes or whatever, then it's usually beneficial to train with all these different supervisions, even though you don't really care about, because this really it's a form of regularization, as we talked about last week, that prevents the network from overfit, and it forces the solution to be more general and hold more information, useful information about the image, about the content of the image.
Shai?
Yeah.
Are there any kind of meaningful differences observed in the features that you learn in the DeepNet, kind of when training with Lambda at 0 as opposed to the other extreme?
I don't think so. We'll talk about visualization of what the network learned next week. Tali will talk about it. I don't think we'll get to this resolution of what is the difference between the same architecture trained only for classification or with multitask. It's an interesting question. I didn't see any work that did this kind of drill down, but you usually see improved in performance. So because this multitask training serves as an additional regularization. Okay, so we solved the first challenge. So we know how to train a network to have multiple types of outputs, both classification and regression. But how are we going to handle the fact that we need to output many objects from a single image, and we don't really know how many are there? So what we can do is version 0 of object detection. We can simply take the image, crop small windows from the image in different shapes, different sizes, different locations, and we can run this localization network that we trained on each and every one of these crops. And if we have a bigger image, we can do the same. We can crop regions, resize them to the fixed size that this image classification and localization network expects, and classify and localize the objects in each and every one of these overlapping windows. And if we want to detect objects in different sizes, we can crop different scales, and if we want different aspect ratios, if we want elongated objects or flattened objects, we can crop these different shapes, resize them to what the network expects, and get the classification and the localization of the objects in these windows. So if we do this and we slide this window over the image, we can get these types of crops, and we apply the network to each and every one of them. And our network localize and classify each and every one of them. And this looks like fine. Sometimes it can be more challenging because the object is not exactly contained in the window, but if our localization network can extrapolate, it can say, well, I see a part of the dog, but it's a very big part, and I can guess quite well where this dog fit in this image. So, but what happens with these kind of images, of image region that the network sees? What kind of prediction do we want our network to give for this kind of crops? So we want to add another class to our 80 classes that we have that says this is background. Basically, this crop doesn't contain any interesting object. We don't really care about this crop. You can discard it. And this is the classification of this object, of this region. What do you think the network should output from the bounding box regression for this crop? Anyone? Okay, so since this is a background object, we don't really care about the bounding box of this crop. So the network can output whatever it wants. We simply don't care. We won't look at it. And if we think about it, most of the crops of the image, if we do as this sliding window crops, most of them would be a background. Only very few of them will contain meaningful, significantly large portions of the object. So to recap, we saw that what makes object detection significantly more difficult than classification is the fact that we have multiple types of outputs, and we don't really know in advance how many objects there are. So multiple type of outputs we solved by multitasking, multitask learning, which is easy. And we can address the number of objects by introducing the background class. So we can classify all the regions, and if there's no significant objects in them, we can simply discard them, and we are left only with the meaningful regions that has objects that we care about in the image. So are we done? Is this really, can we just check object detection? There's still the fact that this is not really feasible. So it's a nice approach. It's very naive, but it's not really feasible. So how many windows are there in an image? So if we are talking about a moderately sized image, not the very tiny 224 by 224, but say 600 by 800, we are talking about roughly 100,000 overlapping windows of size 224, 224. But this is only for a fixed size and fixed aspect ratio. If we want to detect objects in different scale, different sizes, and different shapes, then we'll need to consider all these type of overlapping windows, and we'll end up with easily millions of overlapping windows. And for each and every one of this crop, we need to apply the network to it. So it's a feed-forward classification. So if we want to do detection in a single image, it's like doing classification in the entire ImageNet dataset. So this is not really feasible. We need to come up with a method of doing this in a much more efficient way.
Shai,
Yes.
in the case that you said that this part is a background, you assume that in the dataset you have also background images?
You don't need background images. You are doing the classification. We will see this later on, but you're actually trained on all these possible regions in the image. So you have annotations for the meaningful regions, and you have regions that has no annotations, which basically mean they are background. You don't need anyone to specifically delineate all the possible background regions in an image.
But how the program knows that this is a background?
We'll see that in a few slides. Okay, but basically what we have, as we saw in the second slide, is the annotations you have. You have an image, and you have bounding boxes, or even more accurate masks around the objects, and you have the category of each and every one of the objects. So we have a bounding box around the dog, which says dog, around the cat that said cat, and around the duck that says a duck. And you don't really need to have arbitrary bounding boxes here that says background. We'll see that in a few more slides. So let's try to make things slightly more efficient. So if we look closely at this independent cropping and classification of all these image regions, this is actually a sliding window operation. We apply this network with the two heads on each and every overlapping window of the image. And if we do this by cropping and feeding to the network, this is extremely inefficient. We are already familiar with an efficient way of performing some sort of sliding window operation. Can you think what this is?
Cross correlation.
Cross correlation or a convolution. Thank you, Mayan. Yes, so convolution and pooling and basically most of the operations in this backbone, we can do very efficiently in an overlapping window in the sliding window operation. What we can't do is this fully connected layers, but it's very easy to replace them with a one-by-one convolution. So if we have a linear operation from this feature to 4, and this feature dimension to number of classes, then we can convert them to a one-by-one convolution on this F-dimensional feature map. So we can turn all this network to be a fully convolutional, a network that has only convolution pooling layers, and of course, element-wise activations. And now we can apply it like a convolution on the entire image. So we don't need to explicitly crop regions. We can just apply it as a fully convolutional network. Yes.
I have a question about this one-by-one convolution. For example, would we have the final feature map before applying one-by-one convolution of the size, for example, 32 by 32 by 64, where 64 is the number of channels, and we apply one-by-one convolution that changes the number of channels to 4, but we still need to get a one-dimensional output. Will we have to take the mean?
You won't get one-dimensional output now because you want output for each and every one of these sliding windows.
But so, we want it. We want one-dimensional output, like four element vector. At the output, right?
So if the feature map is F dimension by some spatial dimension now, you'll get a 4-channel output by the same spatial dimensions.
Yeah, that was my question. After that, we'll have to somehow manipulate.
But you don't want, but localization, you wanted to classify and localize for a single window. But now you want to classify and localize for all the windows, overlapping windows in the image. So you don't want a single output. You want many outputs, and we'll see that in a few more slides. So remember that the ultimate objective of detection is not getting a single object out of the image. You want all the objects. So basically, as many as you can.
So what is F here? This is the maximum amount of
F is the feature dimension. So what Rafael had 64 in his question. So this is the feature dimension that the network outputs. I think it's about 1024 in the ResNet, and I think it was even 4000 in VGG. So it's a very high dimensional space, but it's a feature space. Okay.
So W hat here gives only 4 coordinates?
For each and every one of the sliding windows it is applied to. So it gives you the 4 coordinate for one of the windows.
Okay.
Shai?
Yeah.
So in principle, some of these challenges are kind of also relevant to the image classification setting, right? Like somehow there, the fact that there was like one single true label was in some sense an artifact of the data sets that we were working with.
Yes. But it was, image classification was a simplification, like, I don't know if you saw it because we like to do the history from AlexNet, but basically this challenge existed before and people struggled very hard with it before neural networks. So even this very simplified task of we have one object in the image, just tell me what it is, people didn't know how to solve it 10 years ago. So this is why we are still doing image classification, because it's an entry point. But you're right, it's not really interesting. Detection, segmentation are much more interesting because images are more complex and you want to know more about the images than just a single label. Okay, so instead of
Shai?
now, yes.
Can you say again what's a one-by-one convolution? What does it
It's a
mean?
convolution with that basically does a linear mapping from feature F to dimension C for each and every one of the feature vectors in the image. So you have a kernel of size 1, and it's a linear mapping. So instead of explicitly cropping windows and feeding them to the net, we now have a fully convolutional system that can efficiently go over all overlapping windows in the image. So what is the crop size in this case? Anyone?
It would depend on the, I forgot the exact name, but that's the thing you asked us to.
Yeah, the receptive field. Yes.
Receptive field, yes.
Okay, so basically now we are looking at the windows, which are the exactly size of the receptive field of this backbone. And we are sliding them very efficiently over the image, and we can classify and localize objects in each and every one of these overlapping windows.
Shai, I have a question about this actually. If we have a really deep neural network, the receptive field of it will be the entire image, right?
It will be very big, yes.
Yes.
So in image classification, where you have 224 by 224, yes, the receptive field is more often than not larger than the image itself. Then you have padding and etc.
So the output of the one-by-one convolutional layer that predicts the corners of the bounding boxes, like each spatial coordinate of this 4-channeled feature map will work on almost the entire image, right? Is that as intended?
They will see almost the entire image, but they will localize to the object in it according to the supervision we have. So, but yes, there is, so this is much more efficient than this V1 detection using the fully convolutional network is much more efficient than cropping and feeding what we had in V0. But still, we are restricted to regions of the size of the receptive field. And as you alluded, many of you in the questions, the resolution, because of the stride of this network, the resolution here is very, very coarse. So basically, we don't really see all the possible combinations of shifts of different windows, of different sizes, of different aspect ratio. So this is very nice step forward, but it still doesn't solve us very efficiently the problem of object detection. So at this point, there's basically a split in the road between in main approaches or methodologies for object detection. So on the one hand, we have single shot object detections that are using these fully convolutional framework in a single stage, and they are they're using all sorts of tricks and mechanism to overcome this restriction on these strides and size and scale of the receptive field. And it's a single stage detector, SSD, YOLO, you only look once, and there are all kind of meta architectures that do this. On the other hand, there are two shots mechanism, region RCNN, that we'll see in a second, that basically they say, okay, there are millions of possible combinations of sizes, shifts, aspect ratios. Let's try somehow to drastically reduce the number of possible windows. And once we have these reduced set, we can work with it and classify and localize in each and every one of these regions. So while single shot detectors are very fast because they are working in a single forward pass, because they are trying to handle all the possible regions, sizes, aspect ratios, scales at once, they usually suffer from a high false rate. So they are less accurate than the two shots that are slower because they are working in two stages. But since they drastically reduce the number of candidates, they are usually more accurate. So this is basically the trade-off.
What is false rate?
False rate is the number of falses that the network predicts. So if you have a background region and the network fires and says this is a dog, it's a false because the network falsely detected a dog in the background.
So just like a 0-1 loss.
It's yes. So this is basically the classification of the bounding boxes. But what it means is that they are not very accurate. They will predict objects in the background and things like that. And if you really care about it, you will go with this. Okay, so we are going to focus in this talk about this, and we won't talk about the single stage approaches. So let's talk about faster RCNN. It's a work by Gyushik et al., published in NIPS 2015. So how does a two-stage object detector works? So first we compute the deep features of the network as we did before. So we have this image classification network and we have a feature map. And as we already said, the dimensions of these feature maps. So if the image has 3 channels and some dimensions, some spatial dimensions, the feature map will have much more higher dimensions for each and every one of the pixels, but its spatial resolution would be usually much smaller. So we can talk about 1 to 16 stride or 1 to 32 even. So although I show you them in the same resolution here, this is not the case. The feature map is much coarser in its nature. Once we have a feature map that we actually compute very efficiently because it's a single forward pass of the network, we are using a region proposal network, RPN for short, that basically look in a fully convolutional way on the feature map and says, where are the interesting regions that we should look upon in the image? So for instance, for this image, the region proposal network may say, well, look at these regions, they look interesting, you should focus on them. Once we have these regions in the image, it's very easy to translate them to the feature map because despite the fact that the shapes are different, there's a tight link between each pixel in the feature map and the image pixels. Because we know the strides, we know the receptive field, we can easily compute this mapping between image location and location in the feature map. And once we have these regions, these salient and interesting regions in the feature map, we can take each and every one of these regions and apply this classification and bounding box regression to it. Okay, so we are doing classification and bounding box regression for each and every one of the crops, but now we are not doing it for millions of crops, but only for a very smaller set, like a few thousand only. And we are not computing the features for each and every one of these regions from the image to the feature map, which is very inefficient because we need to apply the entire backbone to each and every one of the crops. But we simply take the features that we already compute and we crop them from the feature map. So what we need to apply to each and every one of these regions is only very thin and very shallow classification and bounding box regression heads. Okay, is the overview of the two-stage faster RCNN clear? Because we are going to dive into the details.
Shai, may I have a question?
Yes, of course.
You said that the net can propose different size of crops.
Mm-hmm.
So the size of the feature map of the region of interest of us of the feature map has different shapes, depend on the receptive field. So how do you turn your input to a fixed size?
So how do I go from this
Yes.
elongated to a square? It's
Yes.
cropping and resampling. I resample this region to be a square. So I squish it. It's not ideal, but since we trained these heads on these squished regions, even if we are, for instance, we are trying to detect bottles that are elongated usually, but this classification and regression will always see the bottles squished. They will know how to identify them and how to extract the bounding box in a correct manner.
One more question. When you take, for example, a rectangle, a box in the image, does it after you apply the backbone in the feature map, will it maintain the rectangle shape? Because you said you squish a rectangle to a fixed
So
square.
the backbone is translation equivariant because it's a fully convolutional neural network. So if the image would be larger, then the feature map would be larger accordingly. And there's no, since we're using rectangular convolutions and we use strides, the same strides in the X and Y directions, then we don't change the aspect ratio between the image and the feature map. So elongated box in the image would remain elongated in the feature map. This, after the region proposer network proposes this region, there's a region of interesting pooling layer that actually does this cropping. And this is where it crop and resample the regions. We'll not get into it, but it's an important component of this method.
Shai?
Yes.
But if the backbone is deep enough, then the receptive field of each special location in the output would be basically the entire input image, right? And so you lose the
yes.
So you lose the information about the localization or the spatial information about where the object is located, if any pixel can determine anywhere in the original image.
So since the backbone is translation equivariant, if you shift a bit, it will be noticeable in the feature map. Indeed, if you are trying to localize very small objects, then you might not want to stride that much in the feature space, and we'll get to that later on what we are doing with different scales of objects, if they are scaled significantly different. But right now, it's each and every point pixel in the feature map has a large receptive field, but now we are classifying and localizing it this receptive field, but we can restrict ourselves to a proposal that is significantly smaller. Okay, so let's see how this region proposal network works, and I hope this will answer some of your questions. And I think it's a good point to take a break, and we'll take a 10 minutes break, and we'll resume in 10 past 10. Okay, thank you very much. So before the break, I gave you the overview of the faster RCNN, which is a two-stage image object detection. So the first stage is the RPN that proposes regions where we should look at. And the second stage basically crop and sample the features of each and every one of the regions, and then do this localization, classification, and refinement of the bounding box for each and every one of these regions, of the proposed regions. So let's see how the region proposal network works. So we have an image, and we have the feature map, and as you can see here, the resolution is quite different. So we maintain the aspect ratio, but the resolution is much coarser. And we have a RPN, which is a network with a fixed receptive field. And we wanted to predict regions with different and varying scales and aspect ratio. How are we going to do this? So for each and every feature in the feature map, we are going to ask. So if we consider this features, for each point, we're going to ask about several options of different sizes and aspect ratios. For instance, is this region contains an object? Is this region contains an object? And not all of these regions are going to match an object in the image. But we can ask this in a fully convolutional manner until we find this location and proper aspect ratio that fits to the object in the image. So how are we going to ask these questions in a fully convolutional network? How does it translate? So what we're going to do is this sliding window fully convolutional network. So it's not one by one because we want the receptive field still to be slightly bigger. We want to look at a context around the object, but it's a sliding window. We're going to project it into some intermediate feature dimensions. So we have these features. We want to do a bit more fine tuning of the features for the RPN to work with. And we're going to have these two heads, one that has classification, but this time it's not into each and every object category, but it's a binary classification. Is this an interesting proposal or not? And regression. And we are going to have this classification and regression not for a single output bounding box, but we are going to have anchors like this question we ask. So we are going to ask about a square, about elongated rectangle, about horizontal rectangle, about different scales of these. So for each and every one of these anchors, if we place them at this point, we are going to ask, is this region, is this anchor at this position correspond to an interesting object? And if so, what are roughly the correct bounding box that correspond to this anchor. Okay, so we have 4K regularization outputs and 2K binary classification outputs for each and every one of the sliding window locations of the RPN.
Shai?
Okay, yes.
So it means that for each pixel, I have K anchors?
Yes, for each pixel in the feature map, not in the image. So it's a sliding window on the feature map. This is a much smaller resolution, but still you're going to have K anchors. So in faster RCNN, they used 9. So they used 3 aspect ratios like square, elongated, and horizontal, and 3 scales. And so you have 3 scales times 3 aspect ratios. You have 9 possible anchors for each and every one of the points. So you place these anchors on each and every point like this, and you have the RPN classify each and every one of these proposals. Is it an interesting object or not? And if it's an interesting object, how should we crop the feature map around it?
But Shai, we still have the probability to encounter some object we can't detect in this system. So
what usually happens is that you have, if you have enough anchors that corresponds to the objects in the data set, then you are good. So because you are doing this in a fully convolutional and you don't restrict yourself only to the anchor, you allow for this anchor to be modified. So if you have object that is roughly this size but slightly thinner, then this refinement of the bounding box should help you find it. So you are not restricted to these 9 sizes and aspect ratios. You can do some fine scale correction for them.
I guess
So,
thinner it's okay, but if the object is bigger, so we don't capture it.
So if you have, like this is the biggest proposal you have, and this is the size of the regions, and you have an object that is the entire image, yes, you won't be able to capture it. Or if this is the tiniest bounding box, tiniest anchor you have, and you have object that is really, really tiny, yes, you won't be able to capture it. So you have to tune the scale of the feature map and the scale of the anchors to the problem at hand. And we'll see about scales in a few more slides. So you have some flexibility here because you can propose in different scales, but there's a limit to the range of scales you can do in this fixed feature map. You're right.
Thanks.
Okay.
Question.
So
why are there 2K scores and not 1K?
It's you can think of it as a 1K binary cross entropy with the sigmoid. You can do 2K. I think it's because they used Café, and Café preferred to have two outputs even for binary classification, but it really doesn't matter. So the fact is that you have binary classification here. You can have it with K outputs, or you can have it's a complementary like prediction of the foreground and the background, and they will sum to 1. But yeah, you're right. It doesn't really matter.
Shai?
Yeah.
Can you say how? What's the loss function for the localization?
Okay, we'll see that in a minute. Okay. So how are we going to predict the bounding box coordinates from the anchor? So if this is an anchor and it's placed around this point, for each anchor we have 4 targets, which is the relative position, and its width and height, which basically determines the size and the aspect ratio of the anchor. And if we have a ground truth object, then we have its position and its size. And we want to fit the anchor to the bounding box of the object in the image. So what we need to predict is basically a correction from the coordinates of the anchor to that of the image, of the true x, y, w, h of the true object in the image. So what we are going to learn, we are not going to predict the x, y, w, and h directly. We are going to predict these corrections. So this is what enables us to make predictions that are dependent on the anchors. And we don't need to learn the location of the bounding box. The network doesn't need to learn it from scratch. It only needs to learn how to correct the anchor to best fit the object. And we only use anchors that are close to the object. So all these corrections should be quite small. So, and you see the corrections are scaled by the size of the anchor. So if we have a very large object, we don't really care if it shifts a bit. If we have a very small object and it moves a bit, then we miss the entire object. Then we want the correction to be sensitive to the scale. And we learn the scale in a logarithmic scale, because again, if we have a very small object, then tiny changes are crucial. But if we have a very large object, then tiny changes in the scale are not really crucial. And during inference, we have these predictions of the corrections, and we can easily, given an anchor, output the location and the scale of the object, giving the anchor and the predicted corrections. So this is how we can actually have multiple predictions and make them dependent not only on the location of the image, on the features, but also on the different anchors. So each anchor can make different predictions. So how do we train the RPN in the object detection? So for training, we have images and we have bounding boxes for the objects with the labels of the object. In order to compute the loss, we actually need to assign label not only to the to this box, but also to all the anchors. So this circles back to the question you asked, I don't remember who, at the beginning, where are the background comes from. So we need to assign object label to each and every one of the anchors. As you can guess, there are much more anchors in the output by the RPN than there are objects in the image. So we need to assign a label to each and every one of the anchors. Some of them are going to have the object label. Many of them are going to have the background label. So if the intersection over union, the IOU of the anchor and some ground truth object is over some threshold, and 0.7, we say this anchor is a positive, it's an object, and we want to regress the bounding box of it. And how do we compute the intersection of a union? So if we have this ground truth object and an anchor, then this is the intersection, this is the union, and intersection of the union is just the sizes of these regions. And as you can guess, this value can go between 0, when there's no overlap, the intersection is empty, and it goes all the way up to 1, when the intersection and the unions are the same. So if the object and the anchor precisely overlap, then we have a perfect match. And
but how do you know the object?
so this is during training.
This is all during training.
Yes, this is during training. We know the objects, we know their location, we know everything there is to know. I'm not talking about inference here. So now during training, we have a lot of proposals. We have many anchors, few thousands, and we need to have label for each and every one of them in order to compute the loss. We only have one label in this case, one box and one cat label, and we have many, many anchors. So how are we going to do the training? How are we going to do supervision between this single annotation and all the anchors we have? So we are going to match each and every one of the anchors with all the objects we have annotated in the image. And if we have anchors with intersection over union greater than 0.7, which is not bad at all, then this is a positive anchor.
Why not kind of maintain the information about the magnitude of the intersection instead of kind of arbitrarily thresholding at 0.7?
Because we are now assigning labels to the anchors. So if the anchor has enough overlap with the objects, it contains enough portion of the object, we want this anchor to have information about this object. So we don't really care how the anchor overlap. The prediction the network is going to make, we are not going to look on this overlap in the prediction stage. We are only going to look at the regressed bounding box after the region was cropped and after it was refined again. So this intersection over union, we don't really care about its magnitude, as long as it's significant enough. So if the anchor doesn't overlap the object at all, then it won't be able to predict where the object is, because it doesn't really know. But if it has enough overlap, then it has enough information about the objects, and it can produce the bounding box where to crop the region for the second stage. So we are only talking about the first stage here. So we don't really need to be 100% accurate. We don't really need to be without any misses. So this is only the first stage. We only want to reduce the number of proposals from millions to a few thousand. So if we have enough overlap, then this is a positive. If the anchor has very small overlap or none at all, then with any object in the image, then this is a negative. We want to predict background for this anchor. And some of the anchors that may have intermediate overlap, they show some portions of the objects, we're just going to ignore them. We are not going to compute loss for these anchors at all. And the overall loss for the region proposal network, we are going to check on the number of classified anchors. We are going to compute the cross entropy between their true label, which is either positive or negative, and what our RPN predicted. And for those positive anchors, we are going to have a loss term of how accurate they predicted the location of the object. Okay, so if you recall, for anchors that are background, for regions that are background, we don't really care about the bounding box regression that the network outputs. So it can output whatever it wants. We don't really care. We won't look at it at inference time. So for all the positive and negative anchors, we have cross entropy loss. And for only the positive, we have regression loss. So this is the loss for the training of the RPN. Any questions? Okay, let's move on. We are very behind schedule. So to recap, we have two-stage object detection, the faster RCNN. We have, at the first stage, we have an RPN. Once it proposes regions, we crop them and we apply classification bounding box regression, and we have output the objects in the image. So we had the challenges of object detection of multiple types of output, and we handled this using multitasking. And we have multiple number of objects. We handled it by introducing the background class, and we use the two-stage object detection framework to do it efficiently. And instead of processing millions of regions, we only process a very small subset thanks to the regions proposed by the RPN. So there's two challenges remain. One, you already asked many questions about multiscaling, but there's also the question of imbalance. So when we did image classification, we have 1,000 training image for each and every one of the 1,000 classes. So the classes were evenly balanced in the training set. But now we have a significant imbalanced data set. We have much more negative and background proposals than we have foreground object in the image. So for instance, we can have a few thousand, tens of thousands of negative anchors and only order of tens of actual objects in the image. So how does it affect the cross entropy loss? So this is the binary cross entropy loss. Y is the target, 0 or 1, and P is the object probability between 0 and 1. And suppose we have almost 1,000 negative objects, and suppose we are looking at some instance of the weights and most of them are being correctly classified as background. We have some background classified as object by the RPN, and one of the objects was correctly classified, and we have also some object regions classified as background. So this is one way of classifying 10 objects out of 10,000 possible anchors. How does the cross entropy look like? So suppose we are very confident when we are correct. So in these predictions, and we are very unconfident. So the probability is around 0, but slightly biased towards the wrong side for these mistakes the RPN makes. So for the positive class, for the mistakes we are making, we have 9 mistakes with about log 0.5. And we have a correct classification of the object and almost 10,000 correct classification for the background objects. So these are loss terms computed for the anchors to be classified correctly. These are for the objects that we misclassified. And if you look at the numbers, we'll see that indeed these incur significant loss over this correctly classified, but because we have so many background objects that we classified correctly, this term dominates the loss. So we have loss term for the misclassification we did, but it's outweighed by the sheer number of correctly classified background images. This is the problem of imbalance. So this is about the loss term, but remember, we don't really care about the loss value itself. What we care about is the gradient, because we are doing stochastic gradient descent. So the gradient should tell us how to improve the weights. So let's try to look at the gradient of the binary cross entropy. So this is the gradient of the binary cross entropy for each and every one of these inputs. And if we look at the gradient magnitude for the misclassified anchors, we have this term. And if we look at the gradient of the background, we'll see that although we have gradient for these misclassified that we want to improve, the gradient is dominated by the sheer number of how many examples we have from the background here. So despite the fact that we correctly classified them, what the gradient and what the loss tells us is that, well, you did it with 0.99 confidence, you can do better, you can do 0.999. So instead of focusing on these few mistakes, the cross entropy loss just drives you to do slightly better on these. And since you have so many of these examples of this correctly classified background, we are still going to focus on them. So eventually what we get in this severe case of imbalance is a classifier that says always predict background, because this will, most of the time it will be correct, but it doesn't give you any meaningful object. So this is the problem of class imbalance. It's very acute in the context of object detection and in segmentation that we'll see later on. I hope we'll have time for that. But you can still have it when you have data sets that for classification that are imbalanced. So for instance, if you're using medical images, you have many healthy patients and a very few not healthy, then you have imbalance in classification as well. So what are we going to do about this? So what we can do is we can do negative mining. We can reinstate the balance condition. So we can compute the loss for all the anchors we have, for these 1,000, 10,000 anchors we have. Most of them, as we saw, are going to be true negative, correctly classified as background. Very tiny fractions are going to be correctly classified as foreground. And we're going to have some mistakes as foreground object being classified as background, or and vice versa. But this is the forward path. But instead of computing the gradient for all these examples, we are going to select only a fraction of the examples. So we are going to sort the mistakes we made, and we are going to select only the K hard examples, only those that we made gross mistakes on them, and we're going to compute the gradient only for these K and ignore all the rest. Remember that we already ignored some of the anchors that has intermediate overlap with the object, so we can discard them. And now we are going to ignore even more. So all these objects that were correctly classified, we're simply going to ignore them when we compute the gradient. And now we restore the balance in some sense, and we can optimize the network. And now the network sees balanced data set, and it will not be able to predict only background. It will have to make informative decisions about foreground and background. Any questions about hard negative mining? Since we don't have much time, I won't get into this focal loss. It basically means that it's an approach that instead of changing the data, it will change the loss itself. But you excuse me. So we talked about imbalance. Let's talk about multi-scale. As you already says, if we have objects in significantly different scales. So for instance, if you're trying to do face detection, and you have selfie images with face capturing the entire image, or these group shots where you have tens of participants and very tiny faces, and you still want to be able to use the same architecture to detect this broad range of scales, we need to address this issue, and just introducing more anchors won't cut it. So let's look at these feature maps. So we have an image, we have this backbone, and we have features and convolutions and features and pooling and striding. And we are working usually at the feature map at this very last layer of the network. So as we saw, we trade the resolution of this feature map with semantic values. So we want the receptive field to be very large. So each and every pixel here looks at a large region of the image. So it has rich context. It can make decision based not only on a very tiny window, but looking at not only the object, but the surroundings. So if you want to identify face, we also want to consider if we see a body beneath it, even if we don't explicitly detect it. So the context is important. So what we have here is, as we go deeper in the features, we have larger receptive field and more semantic values. The features are more complex. They are a more complex function of the features that are below them. But the trade-off is that we lose the resolution. So what we can do is, instead of making prediction at this process scale, where we have the most semantic value, we can also do RPN and do predictions on, yeah? Okay, so we can do predictions in these intermediate feature maps where we have finer resolution. But the fact that we are doing it in multiple layers is quite not very productive, because the features are different. So these predictions, these RPN, they cannot share weights. It might be even that the dimension of the feature map here is different than the dimension here. So we need to train RPN for each and every one of these layers, and this is not very good. And furthermore, the features here are not as semantic rich as the features here. So they are cruder features. So it might help us with the scale, but it won't help us with the information we extract. So what we can do is we can use a feature pyramid network. Basically, we compute the features all the way up. We have very rich features here at a very coarse scale. But now we can do top down and bottom up, and now we can do top down features, and we can combine. We can upscale the features from this layer and combine it with features from the corresponding resolution, and we can get semantic information from this feature map and resolution or fine details from this resolution, and have a feature map that has both resolution information and semantic information. And now we can do predictions in these features that we train them to be of the same dimension and of the same context, of the same semantic context. And we can share these predictions and do multi-scale predictions on these feature maps.
Shai?
Yes.
When we upscale the feature maps, okay, do we do like a max pooling, but reverse, we just multiply each pixel twice, or we do interpolation between the pixels?
You can do interpolation, you can do transposed convolution. We'll get to this in a few slides when we talk about segmentation. But you upsample, and then you introduce these fine scales. Okay, so let's recap and conclude. So object detection poses some challenges like imbalanced data and multi-scale processing, and we can tackle it using hard negative mining or modification to the loss function, and using feature pyramid networks that has, eventually they have feature map that has both the resolution and the semantic information of these deeper layers. So let's move on to semantic segmentation. So in semantic segmentation, what we want to do is for each and every pixel in the image, we want to have its semantic class. So we want all these pixels to be classified as dog pixels, all these pixels as cat pixels. These are sofa pixels. And this I can't see. I think it's a monitor. For some reason, it was considered an important class. So how this deep net that makes prediction for each and every one of the pixels is going to look like? So what we can do is version 0. So we have this image, 3 channels by H by W. We can have fully convolutional networks, fully convolutional layers. So if we had 3 channels here, we are going to project it to higher dimension D, but we are going to stay with the same spatial dimensions. So we are not doing any striding, and we are padding the image accordingly. So we don't change the spatial dimensions. We only apply convolutions one on top of the other. So we have simple features and more complex features until eventually we're going to have a per pixel classification by a fully convolutional network. So we have C, the number of classes for each and every one of the pixels. So we have a probability, a class probability for each and every one of the pixels. We're going to take argmax, and this is going to produce us this nice label map. Note that it's very crucial that we have no pooling and no strides in between these layers, because we want to preserve the resolution of the input image. We want the prediction to be of the same size as the input. But what's the problem with this approach?
It's too computationally expensive.
It's not that bad. That's not the problem here. Take a large GPU.
The receptive field is low.
Okay, I didn't see who said it, but yes, the receptive field is very, very small. So what makes the receptive field of the classification of all the backbones we looked very large was due to these striding and pooling layers that we reduce the spatial dimension, and now you're taking a convolution on these small sampled feature map. It actually has, in the image space, it looks at a very large region. We don't have it here. So if the receptive field is very small, it basically means we are classifying the pixels while we effectively look at through a very tiny window. So how this is going to look like? So here are 2 tiny windows in the image. One of them is cat, one of them is dog. And if I hide the image, I think you won't be able to tell which is which. In order to classify this pixel correctly, it's not enough to look at the pixel itself or its very close neighbors. We need the context. We need the semantic information. We need the large receptive field. So if we have this fully convolutional layers, one on top of the other, with no striding, then it will be very difficult or even impossible to make good semantic segmentation network. So the challenge we have here is basically the context or the receptive field versus the resolution. So if we enlarge the receptive field using stride, we lose resolution. If we increase the resolution, if we maintain the resolution, we are left with very small receptive fields that we can't work with. So we are going to use a backbone, a classification backbone that has very large context, very large receptive field. We have a lot of semantic information in these deeper layers. But how are we going to overcome this resolution gap? So one of the first work that dealt with this, it's the fully convolutional networks for semantic segmentation presented in CVPR 2015 by Trevor Darrell and his student. And they suggested to use transposed convolution. So as Asaf mentioned, we have the convolution layer that takes these dense features and project it to a smaller, for each region here, project a pixel. We can do the transpose of the convolution. So from this spaced region, it produced a dense prediction. So we can have a very large transposed convolution that takes a very small, low resolution feature map and produce very high resolution prediction for it. So they introduced a transposed convolution layer here on top of this prediction layer, and use this to predict the full resolution class map. So there is a trade-off between the stride of the net. So if we have a very large stride, like 1 to 32, which is what most classification backbones have, you see that even if you use transposed convolution, you lose a lot of the details of this classification. So we have green for bike and pink for the person riding them. So if you go and you eliminate some of the pooling, some of the strides in the network, and you result with only 8 times stride. So you don't really need to upscale by 32, and only by a factor of 8. Then you see that you can get many of the details compared to the ground truth annotation for this image. So there is a trade-off between the strides and the amount of how upsample you can do. And this is one way of doing this. So we can do this upsampling to use this backbone that has large receptive field and very semantically rich. And then we can upsample using transposed convolution to classify. Another approach is basically to have large receptive field without strides. We can do this using a trust convolution or dilated convolution. So if this, ignore this item for a second, this is a convolution, a regular convolution. So we have this kernel and we have this X, and we look at the X times the weights around the central pixel. But now we can do this dilation. We can space the kernel, and how it's going to look like is like this. So we have a 3x3 kernel, these dark regions, but they are not packed together, but they are spaced. It's like if we take this feature map and we sample it every second location, and we do a packed 3x3 convolution, we'll have the same result for these intermediate pixel. But since we are doing it on all the pixels with the strides, it's like we did this subpixel striding of this lower network. So dilated convolution enables us to stimulate a stride and to simulate a larger receptive field. So how does it look like in the feature space? So if we have an image, we did stride, and then we applied a small kernel, this is what we have. So we lose the resolution. The feature map here is smaller. And if we upsample, this is what we get. We get these dilated, these spaced features in the same resolution. So this is what we have in the naive approach. But if you use dilation, now the kernel is spaced. So it's the same number of weights, but it's larger because we have these spaces, and we can apply it directly to the image. We get the same features in the even space places, but we also get the values in the odd places because we didn't sample. So we can trade sampling and convolution with dilated, which we have in this path, with dilated convolution. So we have the same number of training parameters, but at the cost of more computations, we can get high resolution features that has larger receptive field. And we can do this, we can do different spacing for the kernels. And basically we have multiple kernels looking at larger and larger regions. So they have larger and larger context. And you can have big receptive field without the need to explicitly do stride or pooling. So this is the approach taken by the convolution, the semantic segmentation network architecture called DeepLab. And they have some variants of the DeepLab V1, 2, and 3. And these are the results you get, and you can, if you remember the fully convolutional network, we saw the results for these. The results here are much finer because we are not sampling, we are using the full resolution, and we increase the receptive field using the dilated convolutions. Another approach, it's called UNet, and we'll see in a second why. We have the input image, and we have convolution, striding, convolution, and you see that we have higher feature space, higher feature dimensions, and the height of the rectangle indicates lower and lower spatial dimensions. So this is what we usually have in a classification backbone. We trade resolution with a larger dimension of the features, but we lost the resolution. But what we can do is we can upsample the feature space and have skip connections that will communicate the spatial resolution, the details between these low-level feature maps and these upsampled feature maps. This is very similar to what the feature pyramid network did. So we saw the feature pyramid network for the object detection, and the UNet architecture for segmentation is analogous in a sense. So we trade resolution here using pooling, but we pool the resolution information from the corresponding layers. So we have both the semantic information and the details for when we make the segmentation decisions. So to recap, the challenge in semantic segmentation is basically the trade-off between the resolution, that we need to have fine details in the pixel classification output, but we need semantic information, we need context, we need large receptive field. So we saw the fully convolutional network approach that uses upsampling at once using transposed convolution. We saw the approach of DeepLab that used dilated convolution, basically skip the necessity to downsample, but by dilating the kernels, they can get very large receptive field. And we saw the approach of UNet that is in its core architecture, it's similar to the feature pyramid network that uses skip connections. So it uses pooling to get large receptive fields, but it pulls the fine details from the low resolution, from the high resolution feature maps to get the details for the segmentation. And I'll rush through the instance segmentation, the final task we are going to look at. So in instance segmentation, we want not only to do segmentation to have labeling for each and every one of the pixels, like in semantic segmentation, but we also want to have different labels for the same type of object. So these are all person. So if we were to have semantic segmentation, they were all grouped in a single blob that says person, but we want to know there are different persons here. So we want these pixels to be classified as person, but they should be classified differently than these person pixels. So we want to know they are both persons, but they are different persons in the image. So we can't really solve this semantic segmentation by the approach, this instance segmentation by the semantic segmentation approaches that we just saw, because they will not be able to distinguish between these person pixels and these. There are much more labels here than just the number of classes, because these are all have the same class, but they should have different output, different prediction. So what we need here is basically a combination of the ability of the detection framework to output multiple objects and the ability of semantic segmentation to have per pixel labels. So one way of achieving this is basically combining these two approaches into Mask-RCNN. Again, the same authors of Faster-RCNN. And what we are going to have is we're going to have this two-stage object detection backbone. We are going to have the region proposals first stage, but instead of having just classification and bounding box regression, we are going to have an additional head here that is going to look like a semantic segmentation head that is going to do a segmentation, but not for the entire image, but only for the region. So if we have this region of dog, we are going to segment only this dog. If there are other dogs around here, this semantic segmentation should be able to ignore them and only label as foreground the specific dog pixels. So for each and every one of these detected objects, we are going to have a class, we are going to have the box around it, and we have an accurate mask for each and every one of these objects. And if you put everything together, these are the type of outputs Mask-RCNN produces. So we have bounding boxes for each and every person here on top of the elephant, but we have different masks from this mask head for each and every one of these persons. And again, all these sheeps here, the different utensils on the tablecloth, the chairs, again, persons and bikes, as you can see. And Mask-RCNN is very good both in object detection and the classification. As you can see here, it is able to handle a large range of scales. So these foreground people are significantly larger than these. This can be achieved using the feature pyramid network. And basically,
Shai?
Yes.
Can you just say a few words about kind of the maybe naive approach of reducing instance segmentation to semantic segmentation, which is to create new labels like person 1, person 2, person 3?
So if you introduce these, there are works that try to do this, but it's very difficult because suppose you have, look here at this example, and the ground truth says this is person 1, this is 2, 3, etc. And my network says this is person 2 and this is person 1. So in terms of the prediction, my network is absolutely correct. But in terms of the loss, since I said the ground truth says this is 1 and this is 2, and I said this is 2 and this is 1, the loss is you made a completely bad decision.
But
so,
this seems like a technical challenge that's easy to overcome, right? Like for the classification part.
It's a technical part and it can be overcome. And there are some works that use this like graph coloring techniques and things like that. But it's it has challenges. It's not completely trivial. By all means, Mask-RCNN is not the only way to do instance segmentation, but this is a very successful one. And moreover, this two-stage framework of doing these region proposals and then do some tasks on these regions, like classification, like bounding box regression, like mask segmentation, you can extend it. So for instance, if you want to predict not only the location of faces, but also the locations of the eye, mouth, and nose. So you can have an additional head that for faces output these landmarks. If you want to predict the skeletons, the pose of a person, where it's joints, then you have Mask-RCNN, and you add just an additional head for these person regions. So this is very versatile. So it's good to know about these tasks, about detection, segmentation, and instance segmentation, but we can extrapolate. These methods can be extrapolated to solve more tasks. So to recap, we saw today how to take deep learning beyond image classification, so to more challenging tasks that are not trivially an extension of image classification. But we saw that in all these tasks, we use the backbones. The basic feature extraction part of the network was usually done using a classification network. So it was pre-trained on ImageNet for image classification. It learned meaningful features. And when we did transfer learning by taking these learned features and retrain them to solve more complicated tasks. And we saw how we can use the same features, these deep features. They are very rich, they are very useful, and they can be used not only for classification, but also for segmentation, detections, and whatever. So maybe the task of image classification is not very interesting and it's boring, but it's very, very useful because it's a very, very good starting point of giving you information about what's in the images. And we saw that we can handle varying number of predictions by introducing background labels. And we can saw that we can cope with the receptive field resolution trade-offs, so we can use very large receptive field that has a lot of context, a lot of semantic information, and we can still recover fine details either by upsampling, by feature pyramid network, so UNets that has these skip connections, or by using dilated convolutions. So thank you very much. And next, this week the tutorial will be given by Ben about more advanced PyTorch hands-on you'll need for your exercises. And next week, as I already told you, Tali is going to speak about feature visualization, about probing deep into these networks and see what are they actually learning. So thank you. And if you have more questions, feel free to ask. Saf, I think we can stop the recording.